Ever heard of FALCON? How about Crystal's Dilithium, or maybe even Sphinx Plus? We're launching a video series about post-quantum algorithms in general, and specifically the ones used in Cellframe. Cellframe is a technologically advanced blockchain project tackling scalability issues and, most importantly, the future quantum threat. And we want to kick off this series with FALCON. So what is this acronym all about? It's a digital signature algorithm. This algorithm is resistant to attacks from both today's classical computers and the quantum computers of tomorrow. FALCON is an asymmetric algorithm, a public key system. In this system, there are two keys, a private, secret key, and a public key. You use this private key to create a digital signature, and no one else should ever know it. You use the public key to verify a signature, and you can share it with everyone. The whole point is that it's extremely difficult, if not possible, to figure out the secret key even if you know the public one. And this all hinges on the difficulty of solving a specific mathematical problem. All asymmetric cryptography is built on trapdoor functions, one-way functions with a backdoor. These functions are easy to compute in one direction, but nearly impossible to reverse. Or more accurately, they were impossible to reverse, because quantum computers are about to turn everything upside down. And they will get help from special algorithms, like Shor's algorithm. Shor's algorithm, by the way, is the killer of classical cryptography. Any asymmetric algorithm based on factorization or discrete logarithms is doomed once powerful quantum computers arrive. However, it's not all bad news. There are problems that can withstand an attack from such a computer. One of these is the lattice problem. In mathematics and cryptography, a lattice is an infinite set of points in n-dimensional space, arranged in a regular pattern. They aren't random. They are defined by a set of vectors, A bases. The core challenge is to find a short vector in the multidimensional lattice. The secret key is used to create a short signature for a document. The public key is used to verify that signature, but it cannot be forged. FALCON is exactly this, an asymmetric algorithm based on lattices. The name itself is an acronym for Fast Fourier Lattice-Based Compact Signatures over NTRU. Let's break it down. Fast Fourier. That's the fast Fourier transform, a powerful mathematical algorithm for quickly processing signals, polynomials, and data. Lattice-based. Based on lattices. We just covered that. Compact. This is the main advantage. It generates the smallest digital signatures among all the standardized post-quantum algorithms. NTRU. This is the oldest, simplest, and most elegant lattice-based crypto system, which has proven its resilience over a long time. So what determines a quantum-resistant asymmetric algorithm's strength? The key principle is the complexity of its underlying mathematical problem. Given all its advantages, FALCON is a perfect fit for blockchains. Compactness is a huge deal here. It directly affects network load, transaction fees, meaning economic efficiency, and data transfer speed. Using FALCON can drastically shrink a transaction's size, which massively improves a network's throughput. For example, FALCON increases a transaction size by only about 10 times, whereas Dilithium increases by roughly 40 times. The Cellframe blockchain code integrates signatures based on FALCON. We chose FALCON as one of our core algorithms for our multi-chain platform from the very beginning. This was a strategic choice that defines our platform's architectural advantages. The fact that FALCON is so compact is incredibly important because all post-quantum cryptography is very heavy. FALCON helps us keep transaction and block sizes relatively small and avoids putting unnecessary strain on the network. The Cellframe protocol has quantum threat protection built in by default, guaranteeing quantum security right now.